Good morning, dear students. In our last video, I have discussed with you people how different kind of media, that is dielectrics and conductors, offer impedance to the electromagnetic waves. Now in our current topic, we will find the average value of Poynting vector, or you can say wave intensity, in electromagnetic waves in a conductor. Now we know the flow of energy per second per unit area, that means the intensity of electromagnetic wave in its direction of propagation is determined by the Poynting vector. You know it very well, we have already defined the Poynting vector. So by the definition of Poynting vector, you must say that it is energy flowing per second per unit area in the direction of electromagnetic waves, and its expression is given by equation number 1, S phasor is equal to E phasor cross H phasor. Now here students, now in this chapter, because we are going to discuss about the plane polarized electromagnetic waves only, so I will consider such a wave which is a plane polarized electromagnetic wave and traveling along x-axis. So I have assumed that in this type of wave, the electric field is directed along y-axis and magnetic field is directed along z-axis, so that I can write E phasor as Ey into j cap and H phasor as Hz into k cap. So I'll be using these two values here in equation number 1. I'll get S phasor is equal to simply Ey into Hz into I cap. So taking the magnitude on both sides, I'll get the magnitude of S phasor as Ey into Hz. The average value of the Poynting vector over one time period, it is always given by S average. It is the total value of the instantaneous value of Poynting vector from 0 to time full time period t divided by one time period. So you know that from 0 to t dt is always equal to capital T one time period. So I will rewrite this equation in the form of equation number 4, that is S average is equal to 1 upon t magnitude of S average, the distance integration with respect to time, right? Now I'll be using this equation 4 using the equation number 3. So rewriting equation 4 using equation number 3, I will get S average is equal to 1 upon t 0 to t integration E by Hz, equation number 5. Now here I want to tell you that for conductors we have already derived the expressions for Ey and Hz, and we have proved that there is a phase angle between Ey and Hz which is given by phi equal to pi by 4. That means magnetic field lags behind electric field by an angle phi which is equal to pi by 4. This is what we have proved earlier in our previous topic. So I can write Ey for the conductors as E naught exponential of iota omega t minus gamma x, as well as Hz for the conductors as given by equation number 7. So now I am going to use equations 6 and 7 in equation number 5. I'll get this type of equations. First of all, before using the equations 6 and 7, I will write their real component. Now see students, if I find out its real component for x is equal to 0. If I'll put x is equal to 0, this term becomes 0. Ey becomes E naught exponential of iota omega t. So resolving exponential of iota omega t into cos and sine, I'll get E naught cos omega t plus E naught sine omega t. So taking the real component, I'll get Ey is equal to E naught cos omega t. Similarly here I will put x is equal to 0 just for convenience sake. I'll omit this term and I'm left with H naught exponential of iota omega t minus phi. So again rewriting its real and imaginary components, I'll get the real component as H naught cos omega t minus phi. Now you can use equation 7 and 8 in equation number 5. So I will get this type of equation: S average is equal to 1 upon t from 0 to t E naught cos omega t H naught cos omega t minus phi into dt. So keeping E naught H and H naught outside the integration sign, because being they are constants, I'll get ninth equation. Now I will consider this integrand IT. IT stands for integrants with respect to time. So I'll get 0 to t cos omega t minus phi dt. It is cos omega t, this is cos a minus b, can be expanded as cos a cos b plus sin a sin b. So cos omega t cos phi plus sin omega t sin phi dt. Now again on opening the brackets, you will get this type of equation. Now from this equation, I will write cos square omega t as 1 plus cos 2 omega t divided by 2. This is cos 2a formula. into cos phi as it is dt. Then here I will keep sin phi out of the integration sign. I will multiply twice of sin omega t cos omega t and divide by 2. Now this term can be resolved further into two terms, keeping cos phi outside the integration sign, half outside the integration sign. I will get dt from 0 to t integration. Then from here again I will get cos phi out of the integration sign, cos 2 omega t divided by 2. So I have forgotten over here to write 2. You have to write here as cos phi divided by 2. Alright, cos phi divided by 2, cos 2 omega t into cos phi dt. Then similarly from here I will get this term as sin 2 omega t dt. So dear students, you have already proved that over full time period integration of cos 2 omega t and sin 2 omega t always vanishes. So I directly put these terms as equal to be 0. So I'll simply left with cos phi by 2. dt is the integration is t. So limits from 0 to t. Now put the integration limits. You will get cos phi by 2 capital T minus 0. So I'll get this type of equation which is given by here. See. So it comes out to be cos phi by 2 t minus 0. So it is it comes out to be t by 2 into cos phi. Now using the value of this integrand, equation number 10 in equation number 9, I will get S average is equal to E naught H naught upon t into t by 2 cos phi. So t goes off with t. You are left with E naught into H naught divided by 2 into cos phi. So this is the expression for average value of the Poynting vector in conductors. Here phi must be equal to pi by 4. So you can say rewrite this equation A in terms of equation number 11 also. So both the equations A or 11 represents the average value of Poynting vector, or you can say wave intensity of electromagnetic waves through the conductors. Now I can find this expression in terms of ZC, that is characteristic impedance of the conductors. How can I go for this now? See, we know that characteristic impedance of a conductor to the electromagnetic wave is given by ZC EY phasor upon HZ. Now I will put the values of EY and HZ. EY is equal to E naught exponential of iota omega t minus gamma x, and similarly HZ. Keeping the like terms cancelled, I am left only with in the denominator exponential of minus iota phi. Now exponential of minus iota phi on moving in the numerator, you will get E naught upon H naught into exponential of iota phi. Now exponential of iota phi can be further resolved into cos phi plus iota sin phi, where phi is equal to pi by 4. Now what is the real component of ZC? It is real part of ZC is E naught upon H naught into cos phi. So cross multiplying, you will get E naught cos phi is equal to H naught into real part of ZC. Now I am going to use this equation 13 in my equation number A instead of E naught H cos phi. E naught into cos phi. So using the value of E naught into cos phi from equation number 13 in equation number A, I will simply get S average is equal to H naught divided by 2 into H naught into real part of ZC. This is the value of E naught cos phi. So solving this, I will get S average is equal to half H naught the square into real part of characteristic impedance ZC. This is named as equation number B. So equation B is the average value of Poynting vector, or you can say wave intensity, in terms of the characteristic impedance of the conductor ZC. This is very important topic because sometimes it is there in the exam for the average value of Poynting vector in terms of characteristic impedance of the conductors. Hope you are finding my videos quite easy to understand. Thank you so much.